Hi all, welcome to part 18, module 2, logic system design. So, we were discussing the so-called simplification procedure K-map, and we already saw how to come up with the minimized sum of product as well as minimized product of sum expression using K-map. Now we will see something different in this video lecture, so that will help you to understand the concept that we will discuss in the upcoming lectures, right? So this is something you can think of, like given a K-map like this, uh, find out the Minterm canonical formula. So far we use this K-map only for simplification, right? So you know how to get the minimized SOP form from the K-map. Simply you can make the largest grouping, like this can be one group and this can be another group, right? Only you can't have a group of four ones, or and you can fold and you can have a group like this, and corresponding product term you can write, and you will get the minimum SOP. Now the question is, it's not asking about minimum SOP, but instead they are asking about Minterm canonical formula they are asking. So you have to come up with the standard or the canonical expression. So where the min terms are involved, right? So min terms are SOP and BOS means this product term is enough. Min term particularly means I need all variable in each and every term. Hope you remember that sigma notations, right? So as min term canonical formula, we have the sum of min terms expression, as well as we have the product of max term expressions. They are the canonical expressions. So we are asked to find out the canonical expression, and you can directly write it from the K-map, right? So here there is nothing to. So I just want to remind you, the what we done so far is the minimization, where we are getting the sum of product, where the individual terms are containing minimum number of literals, right? And the terms are also less. But in min term means we need every variable in each term. So what we can do is we can have the smallest grouping, like so don't group or don't try to have the largest grouping. So if you are getting the largest grouping, one of the variable will be eliminated, one or two variable will be eliminated. We don't want it, right? So we want the min terms as it is. So just group them like this, and tell me what is the term corresponding to it, and that is something you know already. So what is this one corresponds to? X, Y, Z, right? So here this rows corresponds to X and columns corresponds to Y and Z. So you can see that they are in the zero form. So this is nothing but X dash, Y dash, Z dash. Or equivalently, this is the min term 0, right? Min term 0. Similarly, what is this? This is our min term min term 4, I think. So what you can write, it's like X, Y bar, Z bar, Y bar, Z bar. So this is nothing but 1, 0, 0, that is min term 4. And similarly, this is another min term we are having. So this is a straightforward writing, but you don't have to confuse it with the other concepts. So K-map is particularly for the simplification, not for this purpose. But this also we can write using K-map. That is what I was trying to say. Okay. So here what it is, 1, 0, 1, right? So X, Y bar, Z. So that is nothing but min term 5. And what is this min term? This corresponds to, you can see that X bar, Y, Z bar, or 0, 1, 0, that is 2, min term 2, right? So this is the corresponding sum of min term is nothing but sigma of 0 is there, 2 is there, 4 is there, 5 is there. You can write it directly straightforward. Similarly, you can write the sum of max term also by grouping or by finding the sum product of sum term corresponding to max term corresponding to those zeros. So 0 you can group and you can write. See, this is what we got, 0, 2, 4, 5, right? Similarly, the same function equivalently you can represent as product of sum. Product of sum is the simplified general term, product of max term particularly, max term. That is a canonical representation. So that is nothing but some pi of. You can tell me what are all the terms corresponding. You have to group the zeros, right? To get the product of max term or to a product of sum, you have to group the zeros. So tell me what is this term corresponds to. So this corresponds to what? You can see that in product of sum you have to just apply the complement way of writing. So just like what we done in max term, so just write the opposite. So just like, so here I am getting X as 0. So you are, if it is 0, you have to take it as it is when it comes to sum term, but in product term you will take the complement, right? So plus what is this? Y again 0 and Z is 1, so you have to take it like this. So this is nothing but, this is 0 0 1. So 0 0 1 is what? This is max term. We used capital letter, right? Max term 1. Max term 1 we are having. Similarly, tell me what is this? This is what? X plus y bar plus z bar. So this is the next product term. So we will multiply all of them finally, right? So this is nothing but x0 1 1, right? 0 1 1 is 3 m3. So like that you can write down. So this is for we have a max term, sorry, we have max term 1, we have a max term 3. Then what is this? This is 6 and 7, right? So you can see that this is, you can write the max term, fine, but I am just noting down the this notation only, that is 1 1 1. This is max term 7 and this is max term 1 1 0, max term 6. So we have a 6 and 7 also. So anything you can write. So this is on direct way or direct use of K-map. So this is something we did with the normal truth table also. So there is nothing special here, but just you have to understand the difference. That is why this is taken, that's all. So you can write down the canonical representation as well as the simplified minimized representation using this, yeah, K-map. Fine. Now what else? So this is another concept. Again, I already told you some miscellaneous concepts we will discuss here, but this will help you in the understanding of the future videos, okay, future lecturing. So that is why. So implication among Boolean function. So what is implication? Again, in proportional logic you studied this implication. You know the meaning. What is I have proportion variables p and q. What does it mean by p implies q? Right. Hope you remember the truth table. P, Q, then P implies Q, how it is behaving. We have cases like true, true. I mean, instead of true, okay, let me write the 0 and 1. Okay, now all are okay for you, right? 0, 0, 0, 1, 1, 0, 1, 1. Now tell me where this implication is going to give me a false, that is a 0. The only one case that is here, right? In all other case, the implication will give you 1. So implication means if the premise something like P is true, the consequence should be true. So that is my requirement. This is something like a conditional promise. Hope you remember from proportional logic. So I am having the promise that if P, then I am promising you this Q, something like that. So here I violated the promise. That is the meaning of 1 0. Means the P is, whenever P is true, I am supposed to make this Q as true, but I am getting Q as false. That means the whole statement is false, right? And in all other case it is fine. Here P is true and the promise is also kept 1 1. Here both are false, fine. The P is false, but still I am giving the promise, something like that. So in all other cases it is evaluating a true, so 1 corresponds to true, and it is giving a value false only when the premise is true and the condition consequence is false, right? So that is something very clear to you. The same thing we are going to see in proportional logic also, in switching theory also. Here we have logic gates and all, you know, the AND operation, OR operation, XOR, NAND, many things we saw already, but implication we didn't so far, because this is not something interested for us by implementing it as a gate and all. So there is no logic gate that corresponds to this implication and all. So no standard logic gate available, but this operation you can think of, right? And this is something we will see why it is relevant, especially in case of K-map in our subsequent discussion. So right now you just understand. So what is the meaning of F1 implies F2? So here P and Q are two proposition. Equivalently in logic system design we have a Boolean functions, right? Boolean function or Boolean expression. So F1 and F2 are two Boolean functions. So we have a Boolean functions F1 comma F2. Now between this F1 and F2, I am saying that the implication holds. What does it mean? So F1 implies F2. This is valid only when, so three statements are given, all are equivalent. The same thing is expressed in three different ways. The first thing is like there is no assignment of value to the n variables that makes F1 equal to 1 and F2 equal to 0. So from where this n is coming? So we are assuming that F1 and F2 are two Boolean function, right? Boolean functions of n variable, right? n variable. It can be a 3 variable function, 4 variable function, like that. So let it be n variable function. So those individual variable you can give value, and accordingly this Boolean function f1 is getting a final truth value or final logical value 1 or 0. And the requirement is that there should not be anything like that 1 and 0. That means this criteria should not be there. If this is true, if this is the case, definitely that P implies Q is not valid, it is not holding, right? So F1 implies F2, that is true only when this particular case is not happening. Then only I can say that F1 implies F2. Hope it is clear. F1, two function, Boolean function F1 and F2, F1 implies F2 only when the three cases hold, like both are 0, 0, 1, 1, 1, all are fine, but 1, 0 is not allowed. That means the assignment of the n variables is giving me a value for F1 as 1, F2 as 0, right? F1 I am evaluating to 1 and F2 I am evaluating to 0. This is something that should not happen. So that is my requirement, right? So I don't want this to happen. There is no such assignment. Okay, fine. Now another way of interpreting it is, whenever f1 equals 1, you can observe here. So let me tell you. Say whenever, so here this P and Q, instead of that I am writing f1 for P and f2 for Q, and equivalently here I am having f1 implies f2. So in P and Q are the proportional variable. I just related with what you know already. But here it is Boolean function f1 and f2. Okay, fine. And the requirement is whenever f1 is 1 or P is 1. So P is 1 in two cases. Right. So P is 1 in two cases. Whenever this f1 is 1, what is my requirement? Definitely this Q or f2 should be 1. This should happen. I don't want f1 to be 1 and f2 to be 0. Or whenever f1 is 1, definitely f2 should be 1. Right. So this is very important. Hope it is clear. Whenever f1 is 1, in any case of this n variable, I am giving some assignment to the n variable and I got that f1 is 1. In that case, definitely the other side f2, the same assignment of n variable, when you are applying to f2, it should be 1. If we are getting f2 as 0, that means f1 implies f2 is invalid right now. So what is the case where this is valid, this one holds? That is what we are discussing, right? So this is another one. Now another way, another interpretation is like, again let me use a different color. See, whenever f2 is 0, so you can see that f2 is 0 in this case, right, in this case and this case, f2 is 0 in this case and in this case. And when f2 is 0, my requirement is if f1 is also 1, means it is not valid, right? So I don't want it. So what I need is whenever this f2 is 0, I want f1 to be 0 for sure. If I am getting f1 to be 1, that is something, this case, I don't want it. Okay, so I need the guarantee that whenever f2 is 0, so these are two ways of, not three ways. Okay, in same statement you can express in a number of ways, right? So on the first one is the direct definition, the requirement we know. When I can say that the implication f1 implies f2 is valid, so that, or the implication holds only when when I observe all the cases, I should not get a case that f1 is 1 and f2 is 0. That should not happen. Or this can be expressed in a very simplified way, that is whenever f1 is 1, so I just have to take care of that case only. Whenever f1 is 1, I don't want f2 to be 0, right? Then it is invalid. Whenever f1 is 1, I want f2 to be 1. So that is the second definition. Similarly, I can interpret the same thing in a different way if I am having some information about f2. So where you will apply the second definition. When I have some information about f1, I can see whether it is hold or not using this definition. But sometimes I will be having information about f2 only. I know that f2 is 0 for sure. Then what I will try to achieve is I will make this f1 0 somehow. Because if f1 is 1, 1 implies 0. That will be invalid. That I don't want, right? So whenever f2 is 0, definitely that f1 has to be 1. Sorry, f1 has to be 0. Hope it is clear. So don't make any confusion. The same statement, actually the second and third one are something like a contrapositive of each other, like P implies Q is equivalent to negation Q implies negation P. Something like that. Okay, so this also again I am linking with your proportional logic. Say P implies Q is equivalent to negation Q implies negation P, right? This, but this is a contrapositive and both are equivalent, that So that is how you are obtaining this statement and this statement. So this is something like both are 1. When you take the contrapositive, this F2 will come first and 1 becomes 0. Similarly, F1 will come next, that 1 becomes 0. So because negation Q and negation P. Okay. So both are equivalent. So now for a Boolean formula we can apply it also for individual Boolean algebraic terms, product term or max term, also this is applicable. So when I can say that one min term or one product term implies another product term. Similarly, what about one max term or one sum term implies another sum term or not, like that you should be able to link it. So some examples are given, and one more concept, this is something, so all these are some miscellaneous concept only, just for your extra information, not only extra, it is needed in our subsequent discussion and all. Covering. So what is mean by covering? When I can say that one function cover another function. Maybe in DBMS and all, there are also functional dependency, those things are coming, I don't know. Right now you are in S3, right? S4 somewhere you will see that subject, and that time also you will see this covering. So this concept is somewhat similar there also. Covering. So when I can say that to one Boolean function covers, you can see that it is covering, right? It is, the other one is completely inside it, something like that. When I can say that one Boolean function covers another one, the requirement is I given two Boolean function f and g, I can say that this is important, f covers g if and only if, and if and only if, the meaning and all. Right, bidirectional, right? It should P if and only if Q. All those things from propositional logic. Whenever P is true, Q should be true. Whenever P is false, Q should be false. Like that, right? In both direction, it is true. P implies Q and Q implies P. That is the meaning. So if and only if, here the requirement is like a G implies F. So whenever G implies F, and when this G implies F is happening, G implies F is happening, and so if this is a case, this is not true, right? So G implies F is happening in all the different 3 cases, just like whenever G is 1, F should be 1. Whenever F is 0, G should be 0. So the second and third definition, hope you remember. So this is where this G implies F is holding. And in that case, I can say that the right hand side, because this from here I am reaching here, right? So whenever this is true, definitely this is true. So this one is covering this one. So that is the way you have to say. Okay. So maybe with example this will be more clear. So right now you understand how to use the term covers. Okay. So you can think about the two Boolean functions. So let the function f be some b dash. The function can be anything, right? And g be another function, say a b dash. Right, and the dot operator, not operator, how these things are working, everything. And now can you tell me whether this b dash covers a b dash or a b dash covers b dash? So you don't apply your so just go with the definition, okay? Don't say like, you may feel like a b dash is bigger, so that is going to cover the smaller one. So don't apply such logic and all, just go with the definition. So what is written, what is our requirement? So for b dash to, so let's see whether this, accordingly we can go back, right? So whether this b dash implies a b dash, or whether this is true, or a b dash implies b dash. So tell me which is true. Okay. So what is my requirement? So if this is the case, is there any situation like, so what I need is, whenever this is 1, I want this to be 1. Can I say like that? I know that b dash is 1. B dash is 1 means b is 0. So about this part. This is 1. Definitely this is 1. But I don't know anything about this a. A can be 0 or 1. What I know is b dash is 1. Whenever b dash is 1, can I say that a b dash is also 1? I can't say, because I don't know anything about a. A is particular Boolean variable, it can assume 0 or 1. If it is assuming 1, definitely a b dash is 1. But I don't know any information about a. So I can't say that a b dash is 1. Okay, so if a is assuming 0, that is not the case. So it is not valid. This is not true, because I can't say like that, because if this will be 1 but this can assume 0, so accordingly this will be violated. So altogether this will evaluate to 0. 1 0, that is not valid in case of implication. Okay. Now what about this? So here what information I am having is a b dash is 1. So definitely a b dash is 1. And this is AND operation, right? AND operation will give you 1 only when, so this is 1, means A is equal to 1 and B dash is equal to 1. So this is for sure. Whenever this left part is 1, I know that as it is AND operation, I want both the individual operands to be 1. So definitely I can say that this is 1. So the second condition is true. Second condition is enough. So just depends on the situation you have to apply second or the third condition. Okay, so here the second condition is enough. I am talking about these conditions. So here we discussed the condition number 1, that is general one. This is condition number 2. This is condition number 3. So this condition number 2 is enough for product terms, for verification of this kind of terms. Fine. So this is true. So what I know is AB dash implies B dash. So as per the definition, if that is the case, then B dash is covering AB dash. Okay, so this is something very important concept, because what is this interpretation on the background? You know, in the K-map, this once you are grouping and you are trying to get the largest group and you are going to write the product term. Sometimes you will get, yes, let's continue. So this is indirectly saying that, B dash and AB dash, assume, so just visualize how these things are coming in the K map. You will group some set of ones and you will get this product term, say, and the B dash is something, a smaller product term, definitely it will be obtained by a bigger cube, right? Similarly, AB dash is slightly bigger product term, so it will be obtained by a smaller cube. So bigger cube is actually covering the smaller cubes. That is the meaning, right? So this is how we can relate this with the, so why this covering? You feel like a smaller term is going to cover a bigger term. That is something difficult for you to think of. So that is why I'm taking something like an analogy. The smaller term is actually produced by a bigger cube in the K map. And this AB dash is a bigger term compared to B dash, and that will definitely be covered by a smaller cube compared to the cube corresponding to B dash. So the bigger cube is actually covering the smaller cube, something like that. Okay, so you can visualize that way. Similarly, here also, this is another example. See, now you can directly say the smaller product term is covering bigger product term, but this A, B dash, that should be there. Bigger in the sense, if you are taking something completely unrelated like X, Y, Z, that is not the case. The bigger one means a superset of it. So, yeah, that is a correct word, term. So, if X and Y are two product term, right, X covers Y, where X and Y are, X comma Y are two product terms. Okay, product terms. So what is my requirement? I want this, then Y is a superset of X. It can be equal also, fine, because in that case, definitely it is true, right? So it is a superset of, it don't need to be a proper superset, it is just a superset of X. So the smaller one is actually covering the bigger one. So when you are looking it as a product term, but when it comes to some term, the opposite thing is happening. So now it is very interesting. See, some term I'm thinking about this. So I just want to know the relation between A plus B dash and B dash. So I have two possibilities, just like this product term. So either this A plus B dash implies this B dash, or so this is one case, and another case is like this B dash can imply A plus B dash. So which is true? That is my question, whether this is true or this is true. So we can find it. So but now you have to think of something. Here it is plus, and when it comes to OR operation, plus operation, plus operation is going to give me 1 in most of the cases, right? So if I am taking the second condition, as per this condition, whenever the F1 is 1, so AND operation, you can use this second criteria, because AND operation will give you 1 in only one case. So only unique case, that means both A and B are 1. In that case only AND is going to give you 1. So you have to check only that case. But when it comes to OR, if you are trying to apply second definition, fine, you can do it. But second definition, if you try, the difficulty is like some 3 cases you have to observe. Just like A, B is giving you 1. When A is equal to 0, B equal to 1, A equal to 1 and B equal to 0, and both are 1. So those 3 cases you have to verify. So that is the difference. So, but when it comes to the false case, that is 0 case, you know that the OR operation is going to give you false in only one case. That means when both the inputs are false, in that case only OR operation is going to give you 1. So it is, see, only one case you have to check. Is that concept is clear to you, or you think about more examples, you will understand. So this is something we can see in proportional logic also. So whenever we have to verify something, implication and all, again this very important one. I don't know in proportional logic how strong you are with the tautology checking. Tautology checking, this idea is very important, because so given some implication, check whether it is tautology or not. So just see what is coming in the left hand side of the implication, right hand side of the implication. If and is coming, typically we will take the second definition and we will check accordingly, because only one case we have to verify. But when that expression involves or operation and all, we have to take the second definition. That means when that f2 is 0, can I get f1 as also 0? So only one case I have to verify. That is why I am going with the third definition. So I am going with the third definition. So by third definition, see what I can do is, I will start with the right side. So I assume that I know that something like b dash is 0. So b dash is 0 means b is equal to 1. Okay. So anyway, this b dash is 0. So what I am obtaining here is b dash is equal to 0. So b dash is equal to 0. Now can I say that a plus b dash is 0? So that is my question. So b dash is 0. Can I say that a plus b dash is 0? No, right? Because this a can assume 1 or 0. I don't have any information about a. What I know is only the right hand side. So we are applying the third definition. Keep that in mind. We are applying the third definition. It is starting like whenever f2 is 0. That is the information I am having. So here the f2 is b dash. Whenever b dash is 0, can I get a plus b dash as 0? No, because a can be 0 or 1. When a is 0, fine, I am getting it as, but I don't know anything about a. So this is invalid. I can't say anything like this. Fine, this is invalid. Now what about this? Again you have to go from the right side to left side, because the contrapositive, third definition we are applying. What I know is this is 0. So this is 0. This is the information I am having, and you know this is important. So why we taken this third definition is because when a bigger expression is 0, the thing is that it is 0 in only one case, that is both inputs are 0. That is, this is 0 on when a is equal to 0, and so I am just telling, this is a statement and I am using, that doesn't mean like or I am writing as and all. Okay, a is equal to 0 and b dash is equal to 0. So this is the only case this a plus b dash is evaluating as 0 for me. So I know very clearly that a plus b dash is 0, or I know that a is 0 and b dash is 0. So definitely this b dash is 0. So this is always valid. See, this is the only thing that is valid. This is invalid. Hope it is clear. Now tell me, if you apply the second definition, what will happen? You have to go from the left side to right side. A plus b dash is 1. Can I say that b dash is equal to 1? So now you have to check the three cases. A plus b dash is 1 in three cases. A is equal to 1 and b dash is equal to 0. A is equal to 0 and b dash is equal to 1. A is equal to 1 and b dash is equal to 1. So those three cases I don't want to check. That is why I go with the third definition. So very important concept. Okay. Fine. So whenever I have to check some implication involving or operation, you have to go with the third definition. Similarly, for and operation or the product term and all, you have to go with the second condition. So that is what I want to tell you. Okay, so that about it. So now what we know is like b dash is implying, or in case a smaller term is implying a bigger term, just opposite to the product term. Okay, so I can say that the bigger term is actually covering the smaller term. So this is something different here. So in our case, this is how it is happening. Okay, so that is per the definition. I am just following the definition only, nothing else. So you don't have to think more on this. This is a definition and I am just applying the definition, and I am seeing like which is covering what. Okay. Similarly, here now you can directly write, you know, this one, this bigger term, the sum term. So this is sum term, right? A plus. So this is a smaller sum term. Bigger sum term is covering smaller sum term, but smaller product term is covering bigger smaller term, product term. So both are different. Okay, so because the implication is happening in that direction, so that is highlighted here. For checking the implies relation or the implication among the product term, you have to go with the second definition. So this is our second definition. Hope you remember. Similarly, for checking the sum term, not the contrapositive checking, you have to do, that is a third definition as per the definition. Hope you remember. If I am writing here, later you may be confused. So product term checking and sum term checking. Sum term checking, you have to go with the third definition, that is this, and product term checking, you have to go with the second criteria as per this list. Okay. clear. Anyways, this covering concept is actually a smaller miscellaneous topic, but still in standard textbooks and all you will see it at K-map and all, especially on the subsequent discussion we are going to have. Okay, so that is somewhat a deeper concept, but still we will see. Fine, thanks for watching.